In this tutorial, we will explore the stereochemistry of addition reactions. For example, if we add X and Y across the following alkene, and let's say we've already decided where the X goes and where the Y goes. Remember, that was an issue of regiochemistry, whether the X ends up on the more substituted carbon or the less substituted carbon. Once you've determined what the regiochemistry of an addition reaction is, we then need to explore the stereochemistry of the addition reaction, because we've created two new stereocenters here. And with two new stereocenters, we expect four possible stereoisomers. Let's draw them all out and compare them. These are the four possible stereoisomers. We have X and Y both on dashes, or X and Y both on wedges. These represent a pair of enantiomers. Then we have X on a dash and Y on a wedge, or X on a wedge and Y on a dash. And these two represent a pair of enantiomers. So we have essentially two pairs of enantiomers, and these are the four possible products. But in general, we won't get all four products. In general, we will either get this pair of enantiomers or this pair of enantiomers. And for each reaction, depending on what X and Y are that we're adding, you need to know which pair of enantiomers you're going to get. When X and Y end up on the same side of the ring, when the two groups that we're adding end up on the same side of the ring, either both on dashes or both on wedges, we call that syn addition. When the X and the Y, the two groups adding, are on opposite sides of the ring, a dash and a wedge, or a wedge and a dash, we call that anti-addition. And again, for every reaction, you need to know whether the reaction proceeds via a syn addition or via an anti-addition. Let's see an example. Consider the following reaction, where we do a hydroboration of the alkene, followed by oxidation. And hydroboration oxidation will add H and OH across the alkene, where H goes on the less substituted carbon and OH goes on the more substituted carbon. So we're going to place an H right here, which we don't have to draw, and an OH right here. Well, let's go ahead and draw that H anyway, even though we don't have to draw it. And we have two new stereocenters here. This is a stereocenter, and this is a stereocenter. And that means that there's four possible products. But we won't get all four possible products. We only get the products that come from a syn addition, because hydroboration oxidation adds H and OH in a syn addition. And therefore, the products that we get are going to look like this, where the H and the OH add in a syn addition, and then there's the other enantiomer, plus, again, the H and the OH on the same side, both on wedges or both on dashes. These two products are the pair of enantiomers that we get from a syn addition. We do not get the pair of enantiomers that would have come from an anti-addition, because hydroboration oxidation goes through syn addition. Now, that might sound like there's memorization here, but you don't need to memorize that hydroboration oxidation goes through syn addition. You need to understand the mechanism of hydroboration oxidation. And when you understand the mechanism, you will understand why it has to be syn addition. Let's see one more example. Let's say we take the same starting alkene and we brominate using Br2. So we're going to add one bromine here and one bromine here. Drawn without stereochemistry, it looks like this, but we need to decide which stereoisomers we get, because this is a stereocenter, this is a stereocenter. That means there's four possible stereoisomers, but we're not going to get all four possible stereoisomers. We're only going to get the pair of enantiomers that come from an anti-addition. this pair of enantiomers. We do not get the pair of enantiomers that come from a syn addition. A lot of students think that these two are the same. This compound here and this compound here are not the same compound. They are a pair of enantiomers. They are not superimposable on one another. If you rotate this molecule around 180 degrees in space, you regenerate the same image. You do not regenerate this image. If you have trouble seeing that, I highly recommend that you make a molecular model of this and make a molecular model of this and carefully compare them. Try to overlap one on top of another. See what happens when you rotate them around in space. This is a very common mistake for students to think these two are the same, when in fact they are not. This is the pair of enantiomers we get from an anti-addition. We do not get the products from a syn addition. How do we know that this is an anti-addition? Once again, don't memorize it. Understand the mechanism of addition of bromine across an alkene, and then you will understand why it needs to be an anti-addition. Now, we should point out that this whole business of syn versus anti-addition is only relevant when you're creating two new stereocenters. When you're creating, for example, one new stereocenter, so let's say we're going to do BH3THF, step 1, and step 2, H2O2 OH minus, hydroboration oxidation. When we do a hydroboration oxidation, we're going to add an H and OH across the alkene. H goes here, OH goes here. Let's draw it out for a second without stereochemistry. This is the product we expect. We added an H right there. This right here is a stereocenter. Methyl, hydrogen, propyl, and hydroxymethyl. We have 4 different groups connected to this carbon atom. This is in fact a stereocenter. But this is not a stereocenter. There's 2 hydrogen atoms here. And therefore, if we're only forming one stereocenter, we don't need to worry about syn and anti-addition. We will get the 2 possible enantiomers. We will get the enantiomer, this enantiomer, plus this enantiomer. We will get a pair of enantiomers, regardless of whether this was syn or anti. We happen to know that hydroboration oxidation goes through a syn addition, but it doesn't matter for this particular example, because even if hydroboration oxidation had gone through an anti-addition, we still would have gotten these 2 products. Syn versus anti is only relevant when we're creating 2 new stereocenters and there's 4 possible products. When we're only creating 1 new stereocenter and there's only 2 possible products, we will get the pair of enantiomers, the 2 possible products, regardless of whether the reaction is syn or anti. And of course, it goes without saying that when we're creating no new stereocenters, for example, if we do hydroboration oxidation again here, the product that we get is going to look like this. There are no new stereocenters. Here we do not even have a pair of enantiomers. So, what you need to do for every single addition reaction, you need to know whether that addition reaction proceeds through a syn addition or through an anti-addition. And the way to remember that is by understanding the mechanism. Then, when you're drawing products of an addition reaction, you need to look and see if you're creating 2 new stereocenters in that particular example. When you're creating 2 new stereocenters, you have to know whether the reaction proceeds through a syn addition or an anti-addition in order to know which pair of enantiomers to draw. If you're only creating 1 new stereocenter, syn versus anti is irrelevant. Just draw both enantiomeric products. If you're not creating any new stereocenters, also syn versus anti is irrelevant. You're just going to get that one product.